We are looking at our first lesson in Chapter 4. It's entitled Organizing Data with Matrices. Our objectives in this lesson are to identify the specific elements of a matrix, to determine the dimensions of a matrix, to use multiple representations of data arrays, and to create a matrix representation for the vertices of a geometric figure. These objectives, we'll do half of them in the first video and probably half in the second video. So let's get started. First, we need to know what a matrix is, and all it is a rectangular collection called an array of numbers. And each number in your matrix is called an element or an entry. And here's what one could look like. You see it's a rectangular figure and you have numbers organized very specifically in that matrix. This matrix is named matrix M. We always name our matrices with a capital letter. And in your matrix, you will have rows, which are horizontal, and columns, which are vertical. Just like a column on a house is always vertical, and rows of like corn in a field are horizontal. So in row 1, you have the elements 2, 4, and 6. In row number 2, you have the elements 3, 7, and 5. And in column 1, you have 2 and 3. Column 2 has the elements 4 and 7. And column 3 has the elements 6 and 5. Well, let's look at our next slide here. Now that we know where our rows and columns are, that actually leads into the dimensions of a matrix. They're in the form m by n, where m is the number of rows and n is the number of columns. So looking back at matrix M, the one we just saw, it would be a 2 by 3 matrix because it had 2 rows and 3 columns. You would denote that as M, the matrix name, and then in subscripts you would write those dimensions, 2 by 3. Let's try to state dimensions for these matrices. Here we have matrix A. Well, to give dimensions, you need to know the number of rows and the number of columns. So count the horizontal and count the vertical. You have 2 rows and you have 2 columns. So this matrix A is a 2 by 2 matrix. Let's try another one. Here, matrix B. To give the dimensions here, we need to again count the rows first. So we have 1, beginning with A, going across. D going across is 2. G going across is 3 rows. And J going across, we have 4 rows. Now let's count our columns. Well, A going down is our first column. B going down is our second column. And C going down is our third column. So we have 4 rows and 3 columns, which means that B is a 4 by 3 matrix. I have some more. Here we have matrix C. This matrix looks a little different from what you've seen so far, but I still want us to take the same approach. Count the number of rows. How many horizontal strips of numbers do we have here? You start at 1 and go across, and that's all. So there is only 1 row. How many columns are there? How many vertical orientations of numbers? Well, there are 4. The first column has number 1, the second column has 4, the third column has 9, and the fourth column has 2. So this is a 1 by 4 matrix, and you would give those dimensions C, matrix C, is a 1 by 4. You put that in the subscript. I have another one kind of like that. Why don't you see if you can count those numbers of rows and columns to give the dimensions. We have 3 rows, X, Y, and Z, each are a row, but we only have 1 column here. Everything is under 1 column. So this would be a 3 by 1 matrix, and D would be denoted as D and then subscript 3 by 1. Now, we have some unique kinds of matrices that, because of their utility, have unique names. One is a row matrix, and it only has 1 row. That gives it its name. You could also have a column matrix, and it will only have 1 column. Or you could have a square matrix because it creates a square due to the equal number of rows and columns. These are all examples that we saw in our previous notes here. A is an example of a square matrix. D was a column matrix, and C is a row matrix. Now you can have matrices that don't fit into these categories, but we do have unique names for these types. Now, we've been calling every element in a matrix just collectively, but we can actually pick out certain ones, and they have unique names. We use subscripts to identify elements in a matrix. So if your element was in row I, column J, in a matrix called A, you would express that as A and then little subscript IJ. Here's an example. We have a matrix A with a capital letter. It's named as such, but each little element in that matrix, which now is expressed with the lowercase a matching, has the subscripts to denote its row and its column position. So A subscript 11 or A subscript 11 is in row 1, column 1. Then next to it you have A subscript 12, row 1, column 2. If you go all the way to that bottom right-hand corner, you have A subscript 33 because it is in your 3rd row and your 3rd column. Let's try to do some of this identification ourselves. So we're going to state the value of each element in this matrix, but we're just going to do certain elements. Our first question is going to be, what is the value of the element B11, also B23, B44, and element B31 or 31. Notice that each of these has the letter B because we are looking at matrix B. So why don't we answer these? First, we're going to find B11. Well, the 1 represents row 1, column 1, and the value there is 3. We look to the next problem, and it's B23. That means row 2, column 3. So you kind of want to go across, find where that intersection happens, and that is the value 14. So element B23 is 14. Also, let's look for B44. That means row 4, column 4, and the value there is 8. Lastly, we have B31. B31. So go to row 3, but the first column So in row 3, look at that first column, and that is 12. So we will write down that B31 is equal to 12. And that's all I have for you guys in this video. Make sure that you write down any questions you have so we can address those together.